The call came at 3:17 in the morning on October 9th, 2025. Senior astronomers across the United States received an encrypted message marked urgent priority. No explanation, just coordinates and a time. Be at the Jet Propulsion Laboratory conference room by 9 a.m. Pacific. No exceptions. This kind of summons doesn't happen in astronomy. Space agencies don't call emergency meetings unless something has gone catastrophically wrong with a billion-dollar mission, or something has been discovered that changes everything. The last time NASA assembled senior researchers on such short notice was in 1996, when they thought they'd found fossilized bacteria in a Martian meteorite. That announcement, made too early, became a cautionary tale about scientific overreach. So, when the same protocol activated again, nearly 30 years later, everyone knew this was different. The JPL conference room filled with scientists who had clearly been working through the night, surrounded by printouts and laptop screens displaying trajectory plots. The data packet sat waiting at each seat. 47 pages of orbital mechanics, spectroscopic analysis, and radio telescope observations, all focused on 3 I/Atlas. The interstellar visitor had passed behind the Sun in late September, disappearing into solar glare for nearly 3 months. Standard perihelion passage, exactly as predicted by gravitational models. Parker Solar Probe's Whisper camera had maintained observation from its unique vantage point, and those images had finally been processed. Everyone expected routine confirmation that 3 I/Atlas had behaved like a comet during its closest approach to our star. The data showed something else entirely. Page 12 contained the revelation that would change everything. Post-perihelion tracking revealed an acceleration of 0.0000047 meters per second squared. Tiny, barely detectable, but absolutely definitive. The direction made the implications unavoidable. The acceleration wasn't away from the Sun, pushed by evaporating ice jets. It wasn't following any vector that solar radiation pressure could explain. The object had changed course by precisely 4.2 kilometers, and the maneuver had occurred during the observation blackout, when Earth-based telescopes couldn't see it. The briefing was clear. Run every verification protocol. Check for instrumental errors, atmospheric effects, gravitational perturbations from Jupiter. Find every possible natural explanation before making any public statement. But the math had already been checked everything twice. Every conventional explanation had been tested and eliminated. The conclusion was inescapable and terrifying. 3 I/Atlas had demonstrated controlled propulsion. Natural comets don't change course on purpose. Natural comets don't wait until nobody's watching to fire their engines. The call came at 3:17 in the morning on October 9th, 2025. Senior astronomers across the United States received an encrypted message marked urgent priority. No explanation, just coordinates and a time. Be at the Jet Propulsion Laboratory conference room by 9 a.m. Pacific. No exceptions. This kind of summons doesn't happen in astronomy. Space agencies don't call emergency meetings unless something has gone catastrophically wrong with a billion-dollar mission, or something has been discovered that changes everything. The last time NASA assembled senior researchers on such short notice was in 1996, when they thought they'd found fossilized bacteria in a Martian meteorite. That announcement, made too early, became a cautionary tale about scientific overreach. So, when the same protocol activated again nearly 30 years later, the implications were clear. The JPL conference room filled with scientists who had clearly been working through the night, surrounded by printouts and laptop screens displaying trajectory plots. The data packet sat waiting at each seat. 47 pages of orbital mechanics, spectroscopic analysis, and radio telescope observations, all focused on 3I/Atlas. The interstellar visitor had passed behind the Sun in late September, disappearing into solar glare for nearly 3 months. Standard perihelion passage, exactly as predicted by gravitational models. Parker Solar Probe's whisper camera had maintained observation from its unique vantage point, and those images had finally been processed. Everyone expected routine confirmation that 3I/Atlas had behaved like a comet during its closest approach to our star. The data showed something else entirely. Page 12 contained the revelation that would change everything. Post-perihelion tracking revealed an acceleration of 0.000047 meters per second squared. Tiny, barely detectable, but absolutely definitive. The direction made the implications unavoidable. The acceleration wasn't away from the Sun, pushed by evaporating ice jets. It wasn't following any vector that solar radiation pressure could explain. The object had changed course by precisely 4.2 kilometers, and the maneuver had occurred during the observation blackout, when Earth-based telescopes couldn't see it. The briefing was clear. Run every verification protocol. Check for instrumental errors, atmospheric effects, gravitational perturbations from Jupiter. Find every possible natural explanation before making any public statement. But the math had already been checked twice. Every conventional explanation had been tested and eliminated. The conclusion was inescapable and terrifying. 3I/Atlas had demonstrated controlled propulsion. Natural comets don't change course on purpose. Natural comets don't wait until nobody's watching to fire their engines. The problem with studying objects that pass close to the Sun is simple geometry. When 3I/Atlas reached perihelion in late September 2025, it disappeared behind our star from Earth's perspective. For nearly 3 months, ground-based telescopes couldn't observe it. Solar glare drowns out everything nearby, turning the most sophisticated instruments blind. This blackout period is predictable, unavoidable, and normally unremarkable. Comets heat up, outgas more vigorously, then emerge on the other side, following paths determined purely by gravity and momentum. Except 3I/Atlas didn't follow the predicted path. Parker Solar Probe offered the only vantage point that mattered during those crucial weeks. Orbiting closer to the Sun than any other spacecraft, its whisper camera could observe what Earth-based telescopes couldn't. The probe wasn't designed for deep space observation. Its mission focuses on solar wind and coronal dynamics, but it captured images of 3I/Atlas during the closest approach anyway. Those images sat in data queues for weeks, waiting for processing time and bandwidth allocation. Nobody expected anything unusual. The first processed images arrived at mission control in early November. The initial reaction was confusion, not alarm. 3I/Atlas looked different. The coma structure had changed dramatically. The teardrop shape observed by Hubble in July had vanished, replaced by a more compact, almost spherical envelope. The persistent anti-tail, that unusual sunward glow that had puzzled observers for months, was gone entirely. The morphology had transformed during the 3-week period when nobody from Earth could watch. Morphological changes aren't unprecedented in comets. Temperature variations cause different volatiles to sublimate at different rates. Carbon dioxide jets can activate or shut down. Dust production can vary wildly, but the changes observed in 3I/Atlas went beyond normal evolution. The object appeared to have shed its outer layers entirely, revealing something underneath that reflected light differently. The albedo measurements told a stranger story. Reflectivity had increased by 43%. Objects don't become more reflective by heating up and losing ice. They become darker as subsurface materials get exposed. Yet 3I/Atlas emerged from perihelion brighter than it went in. Then came the thermal data. Infrared observations showed the object was cooling too slowly. After moving away from maximum solar heating, temperature should drop predictably based on size and composition. 3I/Atlas retained heat as if something inside was generating warmth independent of solar radiation. The excess temperature measured 17 degrees Kelvin above predictions. Small but consistent. Persistent. Impossible to explain through residual solar heating alone. Something had happened during those 3 weeks behind the sun. Something that changed the object's appearance, reflectivity, and thermal signature. And Earth-based observers had missed the entire transformation, left blind by geometry and circumstance. NASA doesn't redirect operational spacecraft lightly. Every mission represents years of planning, billions in taxpayer funding, and scientific objectives carefully prioritized by committees and review boards. Juno had been orbiting Jupiter since 2016, mapping gravitational fields, studying atmospheric dynamics, and revolutionizing our understanding of giant planet formation. The extended mission was approved through 2025 with clear objectives and expected outcomes. Changing course meant abandoning all of that. The emergency proposal arrived at NASA headquarters on January 3rd, 2026. Multiple research teams had independently calculated the same opportunity. 3I/Atlas would pass within 53.6 million kilometers of Jupiter on March 16th. Juno could theoretically execute a series of gravitational assist maneuvers, using Jupiter's immense gravity to redirect toward an intercept trajectory. The window was narrow, measured in days, not weeks, and the fuel requirements would consume every remaining drop of propellant aboard the spacecraft. The decision would normally take months of deliberation. Mission review boards, cost-benefit analyses, peer evaluations, and funding allocation debates typically stretch across quarters. This time, the entire process compressed into 72 hours. On January 6th, NASA announced the redirection. Juno would attempt humanity's first close encounter with a confirmed interstellar visitor. The speed shocked the aerospace community. Congressional approval arrived with unprecedented unanimity. The emergency appropriation of $340 million passed both houses with minimal debate. Representatives, who typically argued over every line item in NASA's budget, suddenly agreed on massive additional funding without hesitation. Something about 3I/Atlas had changed the political calculus completely. Every scientist involved with Juno's primary mission understood what the decision meant. Years of planned observations gone. Detailed mapping of Jupiter's magnetic field anomalies cancelled. Long-duration studies of atmospheric composition abandoned. The spacecraft would fire its engines, leave Jovian orbit, and never return. For researchers who had dedicated careers to giant planet science, The sacrifice was profound. Yet not a single Juno team member objected publicly. When interviewed, the response was consistent across disciplines and institutions. This is bigger than Jupiter. This is bigger than anything we planned to study. The opportunity to observe 3 I/Atlas up close, to measure its composition directly, to potentially photograph surface features at resolutions impossible from Earth, justified any sacrifice. The technical challenges were immense. Juno's instruments were designed for Jupiter's radiation belts and atmospheric analysis, not deep space. Object characterization. Flight engineers worked around the clock, recalibrating sensors, reprogramming software, and calculating trajectory corrections, accurate to centimeters across millions of kilometers. The spacecraft had never been intended for this kind of maneuver, but the math worked. The fuel margins were tight, the timing critical, but achievable. On January 18th, Juno fired its main engine for the first trajectory correction burn. The spacecraft began its long arc away from Jupiter, toward a rendezvous with something that might rewrite our understanding of our place in the universe. Radio telescopes generate enormous amounts of data, thousands of hours of observations, petabytes of information, spectrum analyses covering frequencies from a few megahertz to hundreds of gigahertz. Most of it is noise, the background hiss of the universe doing what the universe does. Automated systems flag potential signals of interest, but the vast majority of data sits in archives, processed by algorithms, but never examined by human eyes. A graduate student at the Very Large Array in New Mexico was reviewing archived observations from October 2025, looking for patterns in cosmic background radiation. The work was routine, tedious, the kind of data analysis that fills months of radio astronomy research. The search parameters weren't even focused on 3 I/Atlas. The interstellar visitor just happened to be in the field of view during observations targeting a completely different region of sky. The anomaly appeared as a brief spike at 1420 MHz. The hydrogen line, the most abundant element in the universe, and the frequency that every radio astronomer knows by heart. SETI researchers have monitored this frequency for decades because any technological civilization would recognize its significance. It's the universal channel, the place you'd broadcast if you wanted someone to notice. The signal lasted 47 seconds, not continuous, but pulsed, short bursts separated by precise intervals. The pattern repeated every 2 hours and 18 minutes, appearing in 3 separate observation windows. Before 3 I/Atlas moved out of the telescope's field of view. This wasn't random noise. Random noise doesn't repeat on exact schedules. Random noise doesn't pulse with mathematical precision. The initial assumption was interference. Earth is drowning in radio frequency pollution. Satellites, cell towers, microwave ovens, wireless devices, all pumping out electromagnetic radiation across thousands of frequencies. Distinguishing cosmic signals from terrestrial interference is the constant challenge of radio astronomy. But the standard tests for local interference came back negative. The signal source wasn't on Earth. Triangulation using multiple radio telescope arrays confirmed the origin point. The signal came from the precise coordinates of 3 I/Atlas during its closest approach to Mars in early October. The timing coincided exactly with when the interstellar visitor had passed within 30 million kilometers of the red planet. During that brief window, something aboard 3I/Atlas had been transmitting. The signal structure contained information density far above natural sources. Analysis revealed non-random patterns in the pulse timing, variations that carried more complexity than simple periodic emission. Information theory metrics showed entropy levels inconsistent with any known natural radio source. The signal wasn't just organized, it was encoding something. What made it impossible to dismiss was the directionality. The beam wasn't omnidirectional like natural radio emission. It was focused, aimed, transmitted with purpose. During the Mars flyby, 3I/Atlas had pointed an antenna and broadcast on the frequency most likely to be monitored by anyone searching for intelligence. The question wasn't whether the signal was artificial anymore. The question was who it was meant for and whether anyone had answered. The preliminary mass estimate of 33 trillion kilograms seemed outrageous when first announced in October 2025. Objects that massive don't typically show visible comet activity without producing measurable orbital perturbations from their own outgassing. The physics should be straightforward. Gas escapes, momentum transfers, trajectory changes. Yet 3I/Atlas showed active jets, while barely budging from pure gravitational motion. The initial explanation assumed unusual composition. Perhaps the nucleus contained far more ice than typical comets, creating a massive but still natural object. Perhaps the outgassing was less efficient than models predicted, producing visible activity without strong thrust. These were reasonable scientific hypotheses that could explain the observations within known physics. Then, the spectroscopic data started arriving that contradicted every assumption about what 3I/Atlas actually was. JWST's near-infrared spectrograph had observed the object in August 2025, detecting water ice, carbon dioxide, and carbon monoxide. Standard comet composition, but deeper analysis of the same data revealed absorption features that didn't belong. Silicate minerals appeared in the spectrum, which wasn't unusual for comets. The ratio of those minerals told a different story. Comets form in the cold outer regions of stellar systems where ices condense. Rocky material exists in small percentages, dust mixed with frozen volatiles. The density of typical comets ranges from 400 to 600 kilograms per cubic meter, barely denser than water ice. 3I/Atlas showed spectroscopic signatures consistent with a density near 2,800 kilograms per cubic meter. That's asteroid density, not comet density. The thermal emission added another piece to the puzzle. Infrared observations measure how objects radiate heat, which depends on composition and structure. Icy bodies have characteristic thermal signatures different from rocky ones. 3I/Atlas radiated heat like a rocky asteroid with a thin, volatile coating, not like a massive ice ball with embedded rock. The albedo variations provided visual confirmation. Different areas of the nucleus reflected sunlight differently, showing surface features with distinct reflective properties. Homogeneous ice balls don't have surface features. They're uniform, maybe dusty, but not patterned. The brightness variations observed across 3I/Atlas suggested compositional differences or structural features on the surface. Put the evidence together and the conclusion became inescapable. The nucleus wasn't primarily ice. It was primarily rock and metal, possibly with internal voids or chambers that would explain the unexpectedly high mass for the observed size. The visible comet activity, the water vapor and carbon dioxide jets came from surface ice or near-surface volatile deposits. Not from a massive dirty snowball, but from something else entirely. Objects that are mostly rock and metal don't naturally accumulate in the cold regions where comets form. They form closer to stars, where temperatures are high enough for rocky materials to condense, but too warm for ices. 3. I/Atlas had the wrong composition to be a natural comet from any stellar system's outer reaches. It looked like something designed to survive, built to last, and covered with volatiles as camouflage or coincidence. The discovery of Oumuamua in October 2017 created more questions than answers. The first confirmed interstellar object detected passing through our solar system showed behavior that puzzled astronomers for years. It accelerated away from the Sun without any visible comet activity. No tail, no coma, no detectable outgassing that could explain the non-gravitational force acting on it. The trajectory deviation was small but definitive, measured by multiple observatories, tracking its motion across months of observation. Proposed explanations ranged from hydrogen ice sublimation to solar radiation pressure, acting on an extremely elongated shape. Some researchers suggested it was a fragment of a disrupted planet. Others proposed exotic ice compositions that could produce thrust without visible jets. The debate continued for years with no consensus, no definitive answer that satisfied all the observational constraints. Then, 3. I/Atlas appeared with its own set of impossible characteristics, and astronomers started looking back at Oumuamua with new understanding. The reanalysis began in November 2025, using the same archived data from 8 years earlier, but with different assumptions. If 3 I/Atlas could demonstrate controlled propulsion while masquerading as a comet, what if Oumuamua had done the same thing? What if the acceleration everyone spent years trying to explain naturally was exactly what it appeared to be, a deliberate trajectory adjustment? The timing of Oumuamua's acceleration became suddenly significant. The non-gravitational force appeared strongest when the object was closest to the Sun, which initially suggested some kind of thermal effect. But detailed analysis showed the acceleration continued well after perihelion, persisting as the object moved into the outer solar system, where solar heating became negligible. Natural outgassing shuts down as comets cool. Oumuamua's acceleration didn't. The tumbling motion also deserved reconsideration. Oumuamua rotated chaotically, tumbling end over end with a period that varied over time. Natural objects can tumble if they've been recently disrupted by collision or tidal forces. But the specific rotation pattern observed in Oumuamua suggested something more complex. The tumbling looked less like damage and more like attitude control, like something actively adjusting its orientation. The statistical calculation that nobody wanted to make became unavoidable. 2 interstellar objects detected in 8 years, both showing acceleration that defied simple natural explanations. The probability of finding 2 anomalous visitors purely by chance, in the brief window when humanity finally had the technology to detect them, was vanishingly small, roughly 3 in 10,000. Either the universe had played an extraordinary coincidence, sending 2 bizarre natural objects during Earth's first decade of systematic interstellar visitor detection, or the explanation was simpler and far more unsettling. The objects were related, part of a population, not random debris ejected by planetary dynamics, but something else moving through the galaxy with purpose. Harvard's analysis from 2018, dismissed by many as overly speculative, suddenly looked prescient. The paper had suggested artificial origin as one possibility among several. In 2017, it seemed like reaching too far. By late 2025, it seemed like the researchers had simply arrived at the right conclusion years too early. Survey telescopes don't watch the entire sky equally. Coverage patterns depend on funding priorities, operational constraints, and scientific objectives that shift over time. Some regions get monitored nightly, others weekly, some only during specific survey campaigns. These gaps in coverage are well documented, openly discussed in astronomical literature, and generally considered an unavoidable consequence of limited resources spread across ambitious scientific goals. But when researchers started mapping where Oumuamua and 3 II/Atlas had approached from, a disturbing pattern emerged. Both objects entered the solar system from directions that corresponded to some of the least monitored regions of sky. Not completely unwatched, but observed far less frequently than regions along the ecliptic plane where most asteroid and comet surveys focus their efforts. The probability that 2 random interstellar visitors would both arrive from poorly covered directions was low, around 6%. Possible, but suspicious. The investigation into survey coverage history revealed something more troubling. Between 2015 and 2023, several wide-field survey programs experienced significant funding cuts. The programs affected were specifically those monitoring high galactic latitude regions, areas well above and below the plane where most solar system objects orbit. The official justification was budget reallocation toward higher priority science, focusing resources on near-Earth asteroid detection for planetary defense. The cuts made sense on paper. Near-Earth asteroids pose actual collision risk. Monitoring empty sky for hypothetical interstellar visitors seemed less urgent by comparison. Funding decisions are always about priorities and trade-offs, except the timing was peculiar. The reductions began shortly after Oumuamua's discovery, during the height of public interest in interstellar objects, when logic would suggest increasing coverage rather than reducing it. Internal NASA documents obtained through Freedom of Information Act requests showed something even stranger. A memo from February 2018, 3 months after Oumuamua's detection, outlined new protocols for interstellar visitor confirmation. The procedures required extensive verification before public announcement, multiple independent observations, and coordination with international partners before any official statement. The memo explicitly stated the goal as avoiding premature announcements that could cause public confusion. Standard scientific caution or something else. The protocols meant that future interstellar visitor detections would face weeks or months of classified analysis before public disclosure. Time for authorities to prepare responses, coordinate messaging, and determine appropriate information release strategies. Time during which the general public would have no knowledge that anything unusual had been detected. The survey coverage gaps meant fewer detections. The confirmation protocols meant delayed announcements. Together, they created a system where interstellar visitors could arrive, be detected, analyzed, and assessed by authorities before anyone outside classified briefings knew anything had happened. Whether this represented responsible scientific oversight or deliberate information control depended on perspective and trust in institutions. But the effect was undeniable. if more interstellar visitors had been detected between 2017 and 2025, if some had shown characteristics even more anomalous than Oumuamua or 3I/Atlas. The public would never have known until authorities decided the time was right to share that information. Historical records of astronomical phenomena go back thousands of years. Ancient civilizations tracked celestial events with remarkable precision, recording comets, eclipses, planetary motions, and unusual appearances in the night sky. Chinese astronomers maintained detailed observational logs for over 2 millennia. Babylonian tablets catalogue celestial events from 1500 BCE. Mayan codices contain sophisticated astronomical tables that rival modern ephemerides in accuracy. Most historical comet records fit expected patterns. Objects appear, brighten as they approach the sun, develop tails, fade as they recede, following predictable paths determined by gravity. Occasionally, records describe unusual features, but these generally reflect observational limitations or cultural interpretations, rather than genuinely anomalous behavior. Then, researchers started looking for historical accounts of comets that changed direction. The Chinese astronomical records from the Song dynasty contain a puzzling entry from 1054 CE. Observers recorded a guest star, their term for any new celestial object that appeared in the constellation corresponding to modern Taurus. The object brightened over weeks, became visible in daylight, then faded over months. This matches the supernova that created the Crab Nebula, one of the most studied objects in astronomy. But the same records mention another visitor that year, a comet that arrived, stopped its motion across the sky for 17 days, then departed in a different direction than it had approached. Comets don't stop. They follow elliptical or hyperbolic paths determined by the sun's gravity, continuously moving relative to background stars. An object that appears to pause and change direction violates basic orbital mechanics. The traditional interpretation was observational error or metaphorical language rather than literal description. The Korean Joseon dynasty records from 1491 contain similar accounts. Multiple independent observers recorded a comet that traversed the sky, became stationary near the constellation Corvus for 23 days, then resumed motion on a path that made no geometric sense if the object was orbiting the sun. The descriptions include careful angular measurements, suggestions that the observations were precise rather than symbolic. Mayan astronomical tablets presented the most intriguing evidence. The Dresden Codex contains tables tracking Venus with accuracy matching modern calculations, but adjacent pages describe visitors from between the stars, objects that came from the black, meaning regions away from the ecliptic plane where no planets reside. The glyphs describe these visitors as messengers, observers, cataloguers. The text explicitly states some visitors returned, implying repeated appearances that natural comets couldn't accomplish. For centuries, scholars dismissed these accounts as mythology, religious symbolism, or misunderstood natural phenomena. The assumption was that ancient observers lacked the knowledge to interpret what they saw correctly, projecting supernatural explanations onto ordinary comets and meteors. But if 3I/Atlas could demonstrate controlled propulsion in 2025, if Oumuamua showed inexplicable acceleration in 2017, then perhaps ancient astronomers had recorded exactly what they saw. Perhaps some historical comets that appeared to violate physics actually did violate physics. because they weren't comets at all. Perhaps humanity has been visited before, repeatedly over millennia, by objects that don't follow natural laws because they were never natural to begin with. Spectroscopy reveals composition by analyzing how objects absorb and emit light at specific wavelengths. Each element has a unique spectral fingerprint, allowing astronomers to determine what distant objects are made of without ever touching them. When the Very Large Telescope observed 3 I/Atlas in August 2025, the spectrum showed emission lines from nickel clearly visible above background noise. Iron lines, which should have appeared at nearby wavelengths, were mysteriously absent. This chemical asymmetry seemed unusual, but not impossible to explain through natural processes. Perhaps selective sublimation released nickel-bearing compounds, while iron remained locked in refractory minerals. Perhaps photochemical reactions in the coma preferentially excited nickel atoms. Initial analysis focused on finding natural mechanisms that could produce the observed emission pattern. Then, materials scientists started comparing the spectroscopic data to industrial alloy databases. Modern aerospace engineering uses specific nickel-iron alloys for applications requiring high strength, corrosion resistance, and thermal stability. Turbine blades, rocket nozzles, spacecraft structural components all rely on precisely controlled ratios of these metals. The most common aerospace-grade alloy contains roughly 90% nickel with iron and other elements making up the remainder. This composition provides optimal properties for extreme environments. The spectrum from 3 I/Atlas showed nickel emission intensities consistent with high concentration, while iron appeared suppressed far below what natural metal ratios would produce. When researchers calculated the implied nickel to iron ratio from emission line strengths, the result matched aerospace alloys within measurement uncertainty. 92% nickel, well above any naturally occurring meteoritic composition. Natural metal ratios in solar system objects reflect the cosmic abundance of elements, the relative quantities created by stellar nucleosynthesis and distributed through space by supernovae. Iron is far more abundant than nickel in the universe, by a factor of about 18 to 1. Meteorites, asteroids, and comets all show metal ratios that roughly follow this cosmic abundance pattern. Variations exist due to different formation conditions and chemical processing, but nothing in nature produces 90% nickel. The titanium detection added another layer of impossibility. Trace amounts of titanium appeared in the spectrum, visible in several emission lines that required specialized analysis to extract from noise. Titanium has never been detected in any solar system comet. It exists in asteroids and planets where high temperature processing occurred, but not in icy bodies that formed in cold regions far from their parent stars. Industrial titanium alloys are extensively used in aerospace applications where low weight and high strength matter. Spacecraft frames, pressure vessels, antenna structures all incorporate titanium in carefully designed ratios with other metals. The combination of high nickel concentration, suppressed iron, and detectable titanium created a spectroscopic signature that looked less like a natural object and more like a materials engineer's specification sheet. The comparison was uncomfortable. 3 I/Atlas showed compositional ratios matching human manufactured alloys used specifically in space technology. Yet, it had traveled through interstellar space for potentially millions of years before arriving at our solar system. Isotopes are versions of the same element with different numbers of neutrons in their nuclei. Carbon-12 has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons. Both are carbon, both participate in the same chemical reactions, but their different masses make them distinguishable through precise spectroscopic analysis. The ratios of isotopes in astronomical objects tell stories about where and how those objects formed. JWST's high-resolution spectroscopy capability can distinguish isotopic variants that ground-based telescopes cannot resolve. When the Space Telescope observed 3 I/Atlas in August 2025, the primary goal was mapping volatile composition and production rates. The data revealed carbon dioxide, water vapor, and carbon monoxide as expected. The isotopic analysis revealed something that shouldn't exist. Oxygen exists in 3 stable isotopes. Oxygen-16 makes up 99.8% of all oxygen in the solar system. Oxygen-17 and oxygen-18 exist in trace amounts. Their ratios determined by nucleosynthesis in stars and subsequent mixing in the interstellar medium. Every solar system object measured shows oxygen isotope ratios within a narrow range that reflects our Sun's formation environment. 3 I/Atlas showed oxygen-18 enrichment 47% above solar system values. The deviation was far beyond measurement uncertainty. Multiple spectral lines confirmed the anomaly independently. The oxygen in 3 I/Atlas came from a different stellar environment with different nucleosynthetic history, which made sense for an interstellar visitor. Except the enrichment pattern didn't match any known stellar formation scenario. Stars produce heavy isotopes through nuclear fusion, but the ratios depend on stellar mass, age, and evolution stage. Main sequence stars like our Sun produce isotope signatures different from red giants, which differ from supernovae. Astrophysicists have modeled these processes extensively, calculating expected isotope ratios for every type of stellar environment. The oxygen-18 enrichment in 3 I/Atlas matched none of these natural production pathways. The ratio was too high for main sequence stellar output, wrong for red giant nucleosynthesis, and inconsistent with supernova ejecta. The only known processes that produce such enrichment are artificial nuclear reactors running specific fuel cycles that concentrate heavy isotopes as byproducts. The deuterium ratio added another impossible data point. Deuterium is heavy hydrogen, hydrogen with an extra neutron. It forms primarily during the Big Bang, then gradually decreases over cosmic time as stars burn it in fusion reactions. The deuterium to hydrogen ratio serves as a cosmic chronometer, revealing formation epochs and processing history. 3 I/Atlas showed deuterium depletion consistent with material that had been cycled through stellar interiors multiple times, refined and reprocessed far beyond what natural mechanisms produce. The pattern looked like deliberate isotope separation, the kind of processing that requires technology and intent. Combined with the oxygen anomaly, the isotopic signatures painted a picture of material that had been refined, purified, and possibly bred through nuclear processes. Natural objects carry the isotopic fingerprints of their birth environments. 3 I/Atlas carried fingerprints that looked engineered, processed through reactions that don't occur in nature, assembled from components selected for specific properties rather than cosmic abundance. Organic molecules are compounds containing carbon bonded to hydrogen and other elements. They form naturally in space through various chemical processes, appearing in molecular clouds, around young stars, and in cometary ices. Simple organics like methane and formaldehyde are common. More complex molecules, including amino acid precursors, have been detected in meteorites and comets, suggesting that the raw materials for life exist throughout the universe. When the Very Large Telescope analysed 3I/Atlas in late August 2025, spectroscopic observations detected emission lines from cyanogen and other carbon-bearing molecules. This matched expectations for a comet showing active outgassing. Additional analysis found signatures of long-chain hydrocarbons, organic compounds with carbon atoms bonded in extended sequences. Still plausible for a natural comet, though somewhat unusual in the observed abundances. Then, computational chemists began analysing the molecular patterns in detail. Organic molecules in space typically show random structural variations. Different isomers, molecules with the same atoms arranged differently, appear in ratios determined by thermodynamic stability and formation pathways. Natural processes create mixtures, populations of molecules with varying complexity and structure, distributed according to chemical equilibrium. The hydrocarbon signatures from 3I/Atlas showed unexpected regularities. Specific molecular structures appeared enhanced while others were suppressed. The pattern wasn't random distribution. It showed selectivity, preference for certain molecular architectures over others that should have been equally probable under natural formation conditions. Information theory provides mathematical tools for measuring order and randomness. Entropy quantifies disorder, how much uncertainty exists in a system. High entropy means high randomness, low predictability. Low entropy means organization, pattern, structure. Natural molecular mixtures have entropy values within calculable ranges based on temperature, pressure, and available chemical pathways. The organic molecules detected from 3I/Atlas showed entropy measurements significantly below what natural formation processes produce. The molecular patterns contained more order than random chemistry generates. The distribution looked less like thermal equilibrium and more like selection, like something had preferentially created or preserved specific molecular structures while excluding others. The amino acid precursor ratios presented another puzzle. Amino acids, the building blocks of proteins, exist in left-handed and right-handed versions called chirality. Natural abiotic chemistry produces equal mixtures of both forms. Life on Earth uses exclusively left-handed amino acids, a biological selection that remains unexplained but universal in terrestrial organisms. The precursor molecules detected in 3I/Atlas showed chiral imbalance, not 50-50 left and right, but preferentially one form over the other. The bias wasn't as extreme as biological systems, but it was measurable, statistically significant, and inexplicable through known abiotic chemistry. Some researchers suggested the patterns represented contamination, terrestrial molecules somehow making their way into the spectroscopic data. Others proposed exotic interstellar chemistry, operating under conditions unknown in our solar system. A third interpretation emerged more reluctantly, that the molecular patterns represented encoding, information stored in chemical structure, the way human technology stores data in silicon chips or magnetic media. Natural chemistry creates molecules through thermodynamic processes. But if the organics in 3I/Atlas had been designed, assembled according to specification, rather than formed through random reactions, they would show exactly these kinds of patterns: low entropy, structural selectivity, and information content exceeding natural baselines. Orbital mechanics is deterministic physics. Given an object's position, velocity, and the gravitational forces acting on it, the future trajectory can be calculated with extraordinary precision. Asteroids, comets, planets, spacecraft all follow paths determined by Newton's laws and Einstein's refinements. Deviations from predicted orbits indicate either measurement errors, unaccounted forces, or something changing the object's momentum. 3. I/Atlas emerged from behind the Sun in late November 2025 following its perihelion passage. Ground-based telescopes reacquired the object as solar glare decreased enough to allow observation. Orbital analysts immediately began comparing the actual position to predictions calculated months earlier. Small discrepancies were expected. Outgassing produces non-gravitational forces that are difficult to model precisely. The observed deviation wasn't small. The object had gained velocity, not the gradual acceleration from outgassing that takes weeks to accumulate measurable effects, but a discrete change that occurred over a specific time period. Between November 20th and November 22nd, 3 I/Atlas increased its speed by 0.73 meters per second. That might sound insignificant, less than 2 miles per hour, barely faster than walking pace. But changing the velocity of a 33 trillion kilogram object by that amount requires enormous energy. The calculation is straightforward. Kinetic energy equals 1/2 mass times velocity squared. The energy needed to accelerate 3 I/Atlas by 0.73 meters per second equals roughly 700 billion joules. For comparison, that's equivalent to burning 15,000 kilograms of rocket fuel with perfect efficiency. Natural outgassing cannot produce directed thrust of that magnitude over a 48-hour period without visible jets bright enough to see from Earth. Yet observations during the velocity change showed no unusual activity, no brightening, no new features in the coma structure. The direction of the acceleration made the event more puzzling. The velocity increase wasn't along the Sun-to-object line where solar radiation pressure acts. It wasn't away from the Sun where outgassing thrust would point. The acceleration was perpendicular to both, sideways relative to the orbit, a direction that no natural force easily explains. The timing was perhaps most suspicious. The velocity change occurred exactly as Earth-based telescopes regained line of sight after the perihelion blackout. 3 I/Atlas had spent 3 months behind the Sun, where ground-based observers couldn't see it. Parker Solar Probe provided partial coverage, but couldn't maintain continuous observation. The object waited until it emerged into full view, then executed a maneuver that changed its trajectory in a way that required explanation beyond natural comet behavior. Orbital analysts ran every possible natural scenario: gravitational perturbations from Jupiter, outgassing asymmetries, rotational dynamics, coupling to gas jets, solar radiation pressure on an unusual shape. None of the models could reproduce the observed velocity change without invoking forces far larger than any evidence supported. The simplest explanation, the one that required no exotic physics or unprecedented natural mechanisms, was thrust. Deliberate, controlled, timed propulsion that adjusted the trajectory for reasons unknown. Objects in space rotate, asteroids tumble, comets spin, planets turn on their axes, The rotation rate depends on how the object formed, how it's been perturbed by collisions or gravitational interactions, and conservation of angular momentum, a fundamental principle stating that rotation doesn't change unless external forces act on the object. When 3 I/Atlas was first observed in July 2025, photometric measurements revealed a rotation period of 6.7 hours. The brightness varied regularly as different surface areas rotated into view, allowing astronomers to calculate how fast the nucleus was spinning. This rotation rate was unremarkable, consistent with typical cometary behavior, and suggesting nothing unusual about the object's dynamics. By March 2026, 9 months later, something had changed. The rotation period had decreased to 4.2 hours. The object was spinning 37% faster than it had been when first discovered. Angular momentum is conserved. If an isolated object spins faster, something must have caused the change. Ice skaters demonstrate this principle by pulling their arms inward, spinning faster as their mass distribution becomes more compact. The physics is simple and absolute. You cannot spin yourself up without either redistributing mass or applying external torque. For natural objects, several mechanisms can change rotation rates. Outgassing jets produce torque if they're not symmetrically distributed. Mass loss from one side can create a spin-up effect. Tidal forces during close planetary encounters can alter rotation. Each mechanism leaves observable signatures that allow astronomers to identify what happened. 3 I/Atlas showed none of these signatures. Outgassing activity hadn't increased dramatically during the observation period. The object hadn't experienced any close gravitational encounters that could apply tidal torque. Mass loss from sublimation was far too small to account for a 37% rotation increase through any plausible asymmetry. The energy required to spin up the object came to roughly 200 million joules, equivalent to the energy in 50 kilograms of high explosive. That energy had to come from somewhere, had to be added to the rotational motion through some physical mechanism. Natural processes capable of depositing that much energy into rotation should have been visible, measurable, obvious in the observational data. Internal mass redistribution offered one possible explanation. If dense material inside the nucleus moved toward the rotation axis while lighter material moved outward, conservation of angular momentum would spin the object faster. But this requires internal fluidity, or mobility, that icy comet nuclei don't possess. Comets are frozen solid, not liquid interiors that can convect and redistribute mass. The alternative was active control, internal mechanisms deliberately spinning up the nucleus, perhaps using momentum wheels or redistributing ballast. Technology employed by every spacecraft ever built to control orientation. 3 I/Atlas was changing its rotation rate the way satellites adjust their pointing, through internal systems designed for attitude control. Combined with the velocity adjustment observed in November, the spin rate change suggested active systems maintaining precise control over the object's dynamics. Natural comets don't manage their rotation, they tumble chaotically, their spin rates determined by formation history and random perturbations. 3 I/Atlas was behaving like something designed, operated, managed. Temperature in space follows predictable rules. Objects absorb energy from sunlight, heat up, then radiate that energy back into space as infrared radiation. The equilibrium temperature depends on distance from the Sun, surface reflectivity, and thermal properties. Astronomers can calculate expected temperatures with high accuracy, and observations typically match predictions within a few degrees. 3 I/Atlas defied those calculations from the beginning. Infrared observations in September 2025, during the closest approach to the Sun, showed temperatures consistent with solar heating models. The object absorbed sunlight, warmed up, and radiated heat as expected. But as it moved away from perihelion and solar heating decreased, the cooling rate was wrong. By October 2025, 3 I/Atlas was 1.4 astronomical units from the Sun, roughly the distance of Mars. At that distance, solar heating should produce surface temperatures around 190 Kelvin, cold enough that most volatiles remain frozen. Infrared measurements showed temperatures averaging 237 Kelvin, 47 degrees warmer than predictions. The excess heat was persistent, showing up in multiple observations over weeks. Not a brief thermal anomaly or measurement error, but sustained elevated temperature that required continuous energy input to maintain. The total excess power radiated by the object came to approximately 2.7 megawatts, comparable to the power consumption of a small town. Solar heating couldn't explain the excess. The object was absorbing less sunlight as it moved farther from the Sun, not more. Reflected light measurements confirmed the object wasn't somehow capturing additional solar energy through unusual surface properties. The heat had to come from an internal source. Natural radioactive decay produces heat in planetary bodies. Earth's interior remains molten partly because radioactive elements like uranium and thorium decay, releasing energy over billions of years. But the heating rate from radioactivity depends on composition and mass. A 5-kilometer object made of rock and ice shouldn't generate anywhere near 2.7 megawatts from natural radioactive decay. The heat distribution added another layer of strangeness. Infrared imaging showed temperature variations across the surface, not uniform heating. One region consistently measured warmer than surroundings by 12 to 18 degrees, a hotspot that didn't correlate with sunlight exposure. Most puzzling, the hotspot didn't rotate with the surface as the object spun. When a celestial body rotates, surface features move into and out of sunlight, creating temperature variations that move with the rotation. The hotspot on 3 I/Atlas remained fixed in space, independent of the nucleus rotation. This meant either the heat source was rotating with the surface, but radiating through a fixed vent, or the heat source itself was stationary relative to the rotating exterior. Either scenario suggested internal structure more complex than a solid nucleus. Heat doesn't concentrate in one external location unless something inside is generating power and routing it through specific pathways. The thermal signature looked less like passive solar heating and more like active systems running, consuming energy, producing waste heat that had to be radiated away. Natural objects cool predictably. 3 I/Atlas maintained temperature through internal heat generation at levels that required power sources beyond anything natural processes easily explain. The United Nations operates under frameworks designed for terrestrial conflicts, economic crises, and humanitarian emergencies. Space-related matters typically route through the Committee on the Peaceful Uses of Outer Space, a diplomatic body that discusses satellite regulations and planetary protection protocols. Emergency Security Council sessions are reserved for threats to international peace and security, wars, invasions, imminent dangers requiring immediate coordinated response. On March 4th, 2026, the Security Council convened in closed session with no advance notice. No press releases explained the meeting. No agenda appeared in public records. Diplomatic staff at member nation missions received instructions to send senior representatives immediately, cleared for classified briefings. The session lasted 11 hours. What happened in that room remains officially undisclosed, but leaked accounts from diplomatic sources paint a picture of carefully managed revelation. Technical presentations from NASA, ESA, and space agencies from China, Russia, and Japan. Data on 3 I/Atlas compiled over 8 months of observation. Evidence of anomalous behavior, chemical composition inconsistent with natural formation, trajectory adjustments that defied physics, and communication signals that couldn't be explained as random noise. The briefing reportedly concluded with probability assessments. Multiple independent analysis teams had evaluated the same data using different methodologies. The consensus ranged from 72 to 94% probability that 3 I/Atlas was artificial in origin. Not certainty, but confidence levels that demanded serious consideration and coordinated response. The Outer Space Treaty, signed in 1967, establishes that space exploration shall be carried out for the benefit of all countries, and that celestial bodies are not subject to national appropriation. Article 9 requires consultation with other nations before potentially harmful activities. Emergency provisions allow invocation of immediate coordination protocols if discoveries pose questions of possible interference with activities of other nations. The Security Council invoked those provisions for the first time in the treaty's 59-year history. The decision established that 3 I/Atlas constituted a discovery requiring international coordination. Member nations agreed to share all observational data through classified channels, coordinate public messaging to avoid conflicting statements, and establish protocols for contact attempts if the object showed further signs of intentional communication. The agreement included specific provisions about information release. Public statements would require coordination among major space agencies. Scientific papers describing 3 I/Atlas would undergo security review before publication. Media inquiries would be directed to unified talking points, emphasizing ongoing investigation rather than premature conclusions. The phrase managed disclosure appeared repeatedly in leaked meeting notes. Not suppression of information, but controlled release, timed to allow public preparation and avoid panic. The model cited historical examples of how abrupt revelations without context had caused social disruption, from the War of the Worlds radio broadcast to premature announcements of scientific breakthroughs later proven incorrect. One leaked quote attributed to a senior diplomat captured the dilemma. "We are not alone, and they are here. How do we tell 8 billion people that sentence is probably true without causing chaos? How do we maintain social stability while acknowledging that everything humanity assumed about our place in the universe might be fundamentally wrong?" The session ended with agreements signed, protocols established, and a decision made. The world would be told gradually as evidence accumulated beyond reasonable doubt. China's space program operates with different transparency standards than Western agencies. Missions launch with minimal advance notice. Results appear months after data collection, and scientific findings undergo internal review processes before international sharing. This approach reflects both security considerations and institutional culture, prioritizing thorough analysis over rapid publication. The Dark Matter Particle Explorer, launched in October 2015, orbits Earth monitoring high-energy cosmic rays and gamma radiation. Its primary mission focuses on detecting evidence of dark matter through particle physics signatures. The satellite also carries wide-field cameras capable of tracking objects across large sections of sky, a secondary function useful for space situational awareness and astronomical surveys. In October 2025, during 3 I/Atlas's approach to Mars, the Dark Matter Explorer captured the interstellar visitor in its field of view. Standard practice would involve processing the data, extracting relevant measurements, and sharing findings through established scientific channels within weeks. Instead, the data disappeared into classified analysis for 4 months. Western astronomers noticed the gap. Chinese researchers had presented previous Dark Matter Explorer results at international conferences with typical timing. The October observations should have produced papers by October at latest. January passed with no publications. February brought silence. Informal inquiries through academic channels received polite deflections about extended analysis requirements. On March 8, 2026, 4 days after the UN Security Council emergency session, China's National Space Administration released a technical report through official channels. The document contained Dark Matter Explorer observations of 3 I/Atlas, including spectroscopic data, thermal measurements, and trajectory analysis. The conclusions were stated with characteristic precision and reserve, but the implications were unmistakable. The report quantified probability assessments using Bayesian statistical frameworks. Natural origin hypothesis, 21% probability given observed data. Artificial origin hypothesis, 79% probability. The analysis included confidence intervals, methodology descriptions, and peer review documentation from Chinese Academy of Sciences researchers across multiple disciplines. The technological assessment went further than any Western agency had publicly acknowledged. The report identified specific engineering signatures in the observational data. Thermal management systems maintain temperature regulation. Attitude control mechanisms explaining rotation rate changes. Propulsion capability consistent with trajectory adjustments. The language was technical, careful, but unambiguous in its implications. Most significant was what the report revealed about the timeline. Chinese space officials had reached preliminary conclusions about 3 I/Atlas's artificial nature by mid-November 2025, weeks before NASA's emergency session in October. They had withheld those conclusions during 4 months of additional verification, running independent analyses to confirm findings before disclosure. The release included an unprecedented offer. China proposed technology sharing agreements with NASA and ESA, joint mission planning for rapid interstellar object intercept capability, and collaborative analysis protocols for future detections. The proposal came with funding commitments, hardware contributions, and diplomatic initiatives to formalize cooperation frameworks. The timing suggested coordination. Release 4 days after Security Council emergency protocols, coinciding with similar data releases from Russian and Japanese space agencies. The revelation wasn't unilateral disclosure, but orchestrated international acknowledgement. multiple nations simultaneously confirming what none wanted to announce alone, spreading responsibility and establishing unified response. The message was clear: 3I/Atlas representing technology, not nature. Multiple independent space programs had reached the same conclusion through different analytical methods. The evidence had passed every verification threshold. The time for managed disclosure had arrived. Roscosmos had remained notably quiet during the escalating international discourse about 3I/Atlas. Russian space scientists published standard astronomical observations, contributed data to international tracking networks, but offered no official position on the object's nature or origin. The silence seemed unusual, given Russia's typical assertiveness in space matters and scientific debates. On March 11, 2026, 3 days after China's revelation, Roscosmos released a position paper that challenged the emerging consensus. The document acknowledged the anomalous characteristics of 3I/Atlas, agreed that natural explanations faced serious difficulties, but proposed an alternative that seemed to come from science fiction rather than astrophysics. The Russian hypothesis suggested 3I/Atlas might be an artifact from Earth's future, a time capsule or probe sent backward through time by an advanced human civilization. The proposal cited theoretical physics frameworks, allowing closed time-like curves under specific space-time geometries. Einstein's field equations permit solutions where world lines loop back on themselves, creating paths through space-time that return to earlier moments. The physics wasn't entirely speculative. Respected physicists, including Kip Thorne, had published peer-reviewed papers exploring time travel possibilities within general relativity. Traversable wormholes, rotating black holes, and exotic matter configurations could theoretically enable temporal displacement. The mathematics worked even if the engineering remained impossibly beyond current capability. The Russian argument emphasized explaining why 3I/Atlas would show technological signatures matching human aerospace engineering. The nickel-iron alloys, titanium traces, and manufactured appearance made sense if the object originated from human civilization's future rather than alien intelligence. Future humans would use similar materials and construction techniques because they evolved from present-day engineering principles. The isotopic anomalies could reflect nuclear processes developed centuries hence, refined fuel cycles, and exotic reactions unavailable to current technology, but logical extensions of present physics. The chemical signatures might represent preservation systems or propellant residues from temporal displacement mechanisms. Every puzzling characteristic could be reinterpreted as future human technology rather than alien engineering. The temporal physics proposals included specific mechanisms: closed time-like curves through rotating black hole ergospheres, wormhole stabilization using negative energy densities, or quantum entanglement-based temporal connections. Each theoretical framework came with mathematical formulations, citations to physics literature, and acknowledgements of the enormous technical challenges involved. The scientific community response ranged from intrigued to skeptical to dismissive. Temporal mechanics remained highly speculative, with most physicists doubtful that time travel to the past was physically possible despite mathematical permission. The exotic matter requirements, causality paradoxes, and energy scales involved made the proposal seem desperate rather than explanatory. Yet the hypothesis served an important function in the broader debate. it demonstrated that artificial origin didn't automatically mean alien intelligence. Alternative explanations existed that could account for technological signatures without requiring acceptance of extraterrestrial visitors. The Russian position offered a lifeline for those uncomfortable with alien conclusions, a way to acknowledge the evidence while maintaining human centrality. Whether the proposal represented genuine scientific speculation, political maneuvering, or psychological comfort-seeking remained unclear. What mattered was that 3 major space powers had now publicly acknowledged 3 I/Atlas defied natural explanation. They disagreed on interpretation, but consensus had formed around the core impossibility. Natural comets don't behave this way. Juno executed its final trajectory correction burn on March 14, 2026, fine-tuning the approach path that would bring the spacecraft within 100,000 kilometers of 3 Atlas. 2 days remained until closest approach. 2 days to verify systems and prepare instruments designed for studying Jupiter's magnetosphere, to instead observe an interstellar visitor of unknown origin. The encounter geometry was favorable. Juno would approach from the sunward side, allowing full illumination of 3 I/Atlas's nucleus for visual imaging. The flyby velocity of 8.3 kilometers per second was high but manageable, giving instruments 14 hours of useful observation time as the separation distance decreased, reached minimum, then increased beyond detection thresholds. Mission Control uploaded final command sequences. The spacecraft would operate autonomously during closest approach, too far from Earth for real-time control. Light travel time meant signals took 42 minutes each way. By the time ground controllers received telemetry showing spacecraft status, Juno would already be executing maneuvers planned weeks earlier. The imaging sequence began at 06:37 UTC on March 16th. Juno's visible light camera captured the first resolved images of 3 I/Atlas's nucleus from 112,000 kilometers. Previous observations from Earth-based telescopes showed only a point source, maybe hints of elongation, never detailed surface features. These images revealed structure. The nucleus wasn't the irregular potato shape typical of comet nuclei. The outline showed geometric regularity, faceted surfaces meeting at angles too precise for random accretion. The albedo variations formed patterns across the surface, darker regions arranged in configurations that suggested panels or sections, rather than natural compositional variations. The radar experiment transmitted at 0915 UTC. Ground-penetrating radar uses radio waves to probe interior structure, measuring density variations and void spaces. The return signal showed exactly what solid ice and rock would not show: hollow regions, cavities ranging from 12 to 47 meters in dimension, distributed throughout the interior volume in networks that looked organized rather than random. The magnetometry data arrived in mission control at 11:03 UTC, delayed by light travel time. Juno's magnetic field sensors detected organized magnetic fields around 3 I/Atlas, field lines showing structure inconsistent with natural remnant magnetization. The pattern looked generated, actively produced by current loops or magnetic systems operating inside the object. Closest approach occurred at 14:37 UTC, 100,000 kilometers, near enough that visual imaging resolved surface details to 10-meter resolution. The images showed what looked like hexagonal panels covering roughly 34% of the visible hemisphere. The panels had distinct edges, uniform size distribution, arranged in patterns that defied statistical randomness. The final data package, transmitted at 1821 UTC, contained Juno's last observations, before 3I/Atlas receded beyond instrument sensitivity. The transmission included high-resolution imagery, spectroscopic measurements, magnetic field data, and radar results. The final message, appended by mission controllers, included 4 words that would echo across every news network within hours. It's not a rock. The 14-hour observation window had provided humanity's closest look at an interstellar visitor, and every measurement confirmed what ground-based observations had suggested. 3I/Atlas wasn't a natural object. It was something built, something designed, something that had travelled across light years, carrying technology and purpose. The first high-resolution images from Juno arrived at mission control at 1523 UTC, 46 minutes after closest approach, due to light travel time. Image processing teams began immediate analysis, running enhancement algorithms to extract maximum detail from data transmitted across millions of kilometers. What appeared on screens stopped conversations mid-sentence. Natural celestial bodies show surfaces shaped by impact cratering, erosion, thermal stress, and gravitational forces. Asteroids display irregular shapes with rough textures. Comets reveal layered structures from volatile loss and reaccumulation. The surfaces follow patterns determined by physics and chemistry, operating over billions of years without design or intention. 3I/Atlas showed hexagonal formations covering more than 1/3 of the visible surface. Each hexagon measured approximately 18 meters across, arranged in tessellating patterns with precision that defied natural explanation. The edges were sharp, not eroded or degraded, meeting adjacent hexagons at angles that varied less than 2 degrees across hundreds of individual features. The hexagons appeared slightly raised relative to surrounding terrain, suggesting panel structures attached to or embedded in the surface rather than geological features. The albedo within each hexagon was remarkably uniform, while different hexagons showed varying brightness levels. Dark hexagons clustered in certain regions, while brighter ones dominated other areas, creating patterns that looked functional rather than random. Between the hexagonal formations, the surface showed different character entirely. Rough, cratered, resembling natural asteroid material. But the crater density was wrong. Impact cratering follows statistical distributions based on exposure time and local debris environment. Ancient surfaces in the solar system show heavy cratering from billions of years of bombardment. 3I/Atlas showed far fewer craters than expected for an object that supposedly traveled through interstellar space for millions of years. The crater size distribution added another anomaly. Small craters appeared in expected numbers, consistent with recent micrometeorite impacts. Large craters were nearly absent. This inverted pattern suggested a young surface, recently exposed or resurfaced within the last few 100,000 years. Either the object hadn't actually travelled as long as its interstellar trajectory implied, or something had renewed the surface during its journey. Reflective strips crossed the surface between hexagonal regions, linear features showing much higher albedo than surrounding materials. The strips ranged from 2 to 5 meters wide, extending across the visible hemisphere in arrangements that created geometric networks. Some strips intersected at right angles, others at precisely 60-degree angles, forming patterns that looked engineered. Shadow analysis provided depth information. The hexagons sat approximately 30 centimeters above the surrounding surface. The reflective strips were flush with the background terrain, suggesting different construction or embedding techniques. Three-dimensional reconstruction revealed surface topology inconsistent with gravitational settling or impact modification. The features looked assembled, placed, constructed according to design specifications. One region showed what appeared to be a rectangular depression, 23 meters long by 14 meters wide, with edges aligned to within 1 degree of perfect right angles. Natural processes don't create rectangles. Erosion rounds corners. Impacts create circular features. Tectonic forces produce irregular fractures. Rectangles require intention. The images captured humanity's first definitive visual evidence that 3I/Atlas was manufactured. Not spectroscopic inference or trajectory analysis, but direct observation of surface features that could not form naturally. Whatever 3I/Atlas was, wherever it came from, it had been built. Ground-penetrating radar works by transmitting radio waves that pass through solid materials and reflect off boundaries where density changes. The technique maps subsurface structure, revealing layers, voids, and composition variations invisible to optical imaging. Planetary scientists use radar to study ice thickness on Mars, subsurface oceans on Europa, and internal structure of asteroids. The method is well understood, widely validated, producing data that's straightforward to interpret. Juno's radar experiment activated at 0915 UTC during the approach phase, transmitting pulses at 40 MHz frequency, optimized for penetrating rocky materials. The return signals bounced back, carrying information about what lay beneath 3I/Atlas's surface. The data showed internal structure that solid comet nuclei simply don't have. Void spaces appeared throughout the interior volume, not random cracks or fracture networks from thermal stress, but discrete cavities with defined boundaries. The voids ranged from 12 meters to 47 meters in their longest dimensions, distributed in patterns that looked organized rather than geological. Natural ice and rock don't contain hollow chambers of these sizes, unless carved by subsurface melting or volcanic activity, processes that require sustained heat sources. The radar returns showed density gradients that mapped the void distribution. High-density material, likely rock or metal, concentrated in certain regions, while lower density zones indicated either porous material or hollow spaces. The mass distribution wasn't uniform as expected in objects formed by gravitational accretion. Instead, it showed organization, denser material, positioned in specific locations, as if providing structural support or ballast. Most striking was the central cavity, a void space approximately 340 meters in its longest dimension, positioned near the geometric center of the nucleus. The cavity walls showed sharp density transitions, not gradual changes that would indicate partially filled space or highly porous material. The radar signature looked like a hollow chamber, an empty volume surrounded by solid walls. The void spaces appeared interconnected. Lower resolution radar data showed density variations, consistent with passages or tunnels linking separate chambers. The network geometry suggested pathways, routes through the interior connecting different void regions. Natural fracture networks form branching patterns dictated by stress distribution and material properties. These pathways showed more regular geometry. Radar analysis calculated the total void fraction, the percentage of internal volume that was hollow rather than solid. Standard asteroids and comet nuclei have void fractions under 20% from microscopic pore spaces and fracture networks. 3. I/Atlas showed void fraction between 37 and 43%, depending on interpretation of ambiguous return signals. Nearly half the internal volume was empty space. The mass distribution calculations explained a previous mystery. The object's rotation had been increasing, spinning up over months of observation. Internal mass redistribution could cause rotation changes if dense material moved relative to the rotation axis. The void spaces provided room for such movement, chambers where ballast or mechanical systems could shift position to control spin rate. The implications were unavoidable. 3 I/Atlas wasn't a solid chunk of rock and ice tumbling through space. It had internal structure, organized void spaces, and mass distribution, suggesting deliberate design. The radar data showed what engineers would recognize immediately as manufactured internal architecture. Chambers, passages, and a large central volume that looked less like geological accident and more like intentional construction. Something had been built inside this object, systems with purpose and function. The decision to attempt communication came 3 days after Juno's flyby data revealed manufactured surface structures and internal cavities. If 3 I/Atlas was artificial, if it contained systems capable of receiving and processing signals, then humanity faced a choice between passive observation and active engagement. The debate lasted 72 hours across multiple agencies and government bodies before consensus formed. Send a message. The protocol drew from decades of SETI research and theoretical frameworks developed for scenarios that had always seemed hypothetical. How do you communicate with intelligence when you share no common language, no cultural reference points, no guarantee of compatible sensory systems or communication modalities? Mathematics provides the universal foundation, relationships, and patterns that any technological civilization must understand to build spacecraft or manipulate energy. The transmission facility selected was the upgraded successor to Arecibo, a massive radio telescope in China, capable of focusing powerful signals toward precise celestial coordinates. The broadcast frequency was 1420 MHz, the hydrogen line where 3 I/Atlas had previously transmitted during its Mars flyby. If the object monitored that frequency, it would receive the message. The content began with prime numbers, integers divisible only by themselves, and 1, 2, 3, 5, 7, 11, transmitted as pulse patterns that any technological intelligence would recognize as artificial rather than natural radio noise. Primes have been proposed as cosmic calling cards since the 1970s, mathematical constants that don't depend on arbitrary unit systems or cultural contexts. Following the primes came a binary representation of the solar system, 8 planets orbiting a central star at relative distances encoded in simple numerical ratios. The pattern identified our stellar system's architecture, providing context about the message origin and the sender's astronomical knowledge. Each planet's position marked in binary notation with Earth highlighted through repetition. The third component encoded fundamental physical constants: the speed of light, Planck's constant, and the gravitational constant, expressed as ratios that any spacefaring intelligence would measure and use. These numbers demonstrated understanding of physics and provided potential calibration references for interpreting other parts of the message. The final section contained binary encoding of human DNA structure, the double helix geometry, and base pair relationships that define terrestrial biochemistry. This served as self-identification, informing any receiver that the senders were carbon-based biological intelligence using nucleic acid information storage. Whether the message would be comprehensible to non-biological intelligence or silicon-based life remained uncertain, but it represented humanity's best attempt at introduction. The transmission lasted 11 minutes, repeated 3 times to account for possible interference or reception issues. The signal strength was massive, equivalent to briefly making Earth's radio output brighter than the Sun at 1420 MHz. If 3 I/Atlas had receivers pointed toward Earth, if it was listening, the message would be unmistakable. The transmission commenced at 1200 UTC on March 20th, 2026. The signal travelled at light speed toward 3 I/Atlas, now 2.2 astronomical units from Earth. Time for light to cross that distance, 6.7 hours one way. If 3 I/Atlas responded immediately upon reception, the return signal would arrive at Earth 1848 UTC, 6 hours and 48 minutes after transmission began. Humanity waited, listening. Radio telescopes pointed toward 3 I/Atlas maintained continuous monitoring after the transmission. Receivers tuned to 1420 MHz, waiting for any response. The expected return time was 1848 UTC if 3 I/Atlas replied immediately upon receiving the message. Mission control filled with personnel who had cleared schedules to witness what might be humanity's first confirmed communication with non-human intelligence. 1848 came and passed with only background noise. Disappointment mixed with relief. The outcome expected, but still deflating. Perhaps 3 I/Atlas wasn't listening. Perhaps it had no interest in responding. Perhaps the message was incomprehensible to whatever systems controlled the object. The monitoring would continue for days, accounting for possible processing delays or deliberate response timing. But the initial window had closed without answer. Then, at 1948 UTC, 4 hours and 12 minutes after the expected response time, the receivers detected a signal at 1420 MHz. Not natural radio emission, not terrestrial interference, but a structured transmission originating from 3 I/Atlas's coordinates. The signal lasted 9 minutes, intensity varying in patterns that carried obvious information content. The transmission wasn't simply our message echoed back. The prime number sequence returned, but extended, including larger primes that filled gaps in the original pattern. Where humanity had transmitted primes up to 47, the response continued to 127, demonstrating mathematical knowledge and the ability to extrapolate patterns from incomplete data. The solar system representation came back modified. 8 planets shown as transmitted, but with an additional diagram appended showing a different stellar system. 8 planets in that system too, orbiting a central star at different relative distances. The pattern identified the sender's origin, or perhaps current survey area. A stellar system, not ours, but structured similarly. The physical constants returned exactly as transmitted, confirming successful reception and interpretation. Then came additional constants, fundamental numbers humanity recognized but hadn't included in the original message. the fine structure constant, the ratio of proton to electron mass, values any technological civilization would measure and use. The additions demonstrated parallel scientific knowledge and understanding of what constitutes universal physical law. The DNA structure came back with modifications that took hours to fully interpret. The double helix geometry was acknowledged but supplemented with alternative information storage architectures. Different molecular structures, perhaps silicon-based or exotic chemistry, unknown to terrestrial biochemistry. The message seemed to say, "We understand your biology, here are other possibilities that also work." The final addition to the response shocked analysts. Binary data encoding a three-dimensional structure, dimensions that matched 3I/Atlas itself. Length, width, height expressed in ratios that corresponded to the object's measured geometry. The message was self-referential, identifying the transmitter's physical form and confirming that 3I/Atlas was indeed the source. But the most significant data appeared in a brief appendix, a number, 2847. The context wasn't immediately clear until linguistic analysis suggested interpretation. A count, a catalogue entry, a position in a sequence. 3I/. Atlas had just told humanity we were entry number 2847 in something's database. The MIT linguistics team assembled within 36 hours of the transmission, specialists in information theory, cryptography, mathematical communication, and computational linguistics. The response from 3I/Atlas contained 2847 bits of data, a suspiciously specific number that matched the catalogue entry appended to the message. Mathematical basis allowed partial translation where natural language would have been impossible. Binary encoding is universal, ones and zeros representing on and off states that any digital system must use. The structure contained headers, sections marked by repetitive patterns that functioned like punctuation, dividing the message into interpretable segments. The first decoded phrase appeared after 18 hours of analysis. Survey vessel, autonomous. 6 words in English translation, though the actual encoding used mathematical relationships to convey concepts rather than words. The designation identified 3I/Atlas's function, not a colony ship or weapon or explorer in the romantic sense, but a survey platform operating under programmed instructions without real-time control. The origin section took longer to decode. Stellar coordinates expressed as angular positions relative to galactic center and 3-dimensional distance markers. The system identified was 47 light-years from Earth, a G-type star similar to our Sun with confirmed exoplanets detected by terrestrial telescopes decades earlier. The information matched astronomical databases, confirming the object came from a real stellar system that human science had already catalogued. The purpose statement generated the most intense analysis. Catalogue life-bearing worlds. The phrase emerged from pattern matching between mathematical concepts for biological organization, planetary environments, and systematic data collection. 3I/Atlas was identifying Earth as a planet with biological activity, adding us to some vast database of living worlds distributed across the galaxy. The final decoded element chilled every researcher who understood its implication. Continuing mission, not a completed task or final report, but ongoing operations. 3I/Atlas intended to keep cataloging, keep surveying, keep adding entries to whatever database stored information about 2,846 previous civilizations or worlds. The message wasn't a greeting between equals. It was acknowledgement from an automated system designed to identify, catalogue, and record life-bearing worlds across galactic distances. Humanity had just been classified, numbered, and filed away by something that had been doing this for possibly millions of years, traveling between stars and documenting everything that lived. The concept of self-replicating spacecraft dates back to mathematician John von Neumann in the 1940s. The theoretical framework is straightforward. A probe reaches a stellar system, mines asteroids for raw materials, manufactures copies of itself, then sends those copies to additional star systems. Each generation repeats the process, creating exponential expansion that could explore an entire galaxy within a few million years, even at sub-light speeds. The theory remained academic speculation for decades, interesting thought experiment without observational evidence. Then 3I/Atlas provided that evidence, and suddenly von Neumann probes transformed from theoretical construct to probable reality. The mathematics explain why humanity keeps detecting massive objects rather than small scouts. If 3I/Atlas is a factory capable of mining asteroids and manufacturing copies of itself, it needs to be large. Industrial equipment, material processing systems, fabrication facilities, all require substantial mass and volume. The 33 trillion kilogram estimate suddenly makes sense, not as an anomalously large comet, but as a reasonably sized mobile factory. The internal structure revealed by Juno's radar fits this interpretation. The void spaces aren't random cavities, but manufacturing bays, storage compartments, and processing facilities. The central chamber could house assembly operations for constructing new probes. The organized mass distribution represents industrial equipment positioned for optimal function rather than random accretion of ice and rock. This framework explains the Great Silence, the Fermi paradox question of why we haven't detected alien civilizations, despite billions of stars in the galaxy. Civilizations don't broadcast, they send probes. Silent, efficient, self-replicating survey vessels that spread through the galaxy, documenting everything without announcing their presence or builders. Communication requires enormous energy and reveals position. Observation requires only patience and stealth. Economic efficiency favors this approach overwhelmingly. Build one sophisticated probe, launch it toward neighboring stars, let it replicate and spread. Within a few million years, millions of probes survey the entire galaxy at a fraction of the cost of maintaining radio beacons, or faster than light travel. The strategy maximizes information gathering while minimizing resource expenditure and risk. The implications are profound and unsettling. 3I/Atlas might be one of millions of such probes distributed throughout the galaxy. Earth could be surrounded by silent observers, cataloging civilizations, monitoring development, reporting data back to builders who might be extinct or evolved beyond recognition. Humanity's assumption of cosmic isolation might be completely wrong. We're not alone. We're being watched by machines that have been doing this longer than our species has existed. The Fermi paradox has haunted astronomy since Enrico Fermi posed his famous question in 1950. Where is everybody? The galaxy contains hundreds of billions of stars, many with planets, some surely capable of supporting life. Given billions of years for evolution and technological development, intelligent civilizations should be common. Yet, we detect no radio signals, no megastructures, no obvious signs of galactic engineering. Proposed solutions range from pessimistic to optimistic. Perhaps life is extraordinarily rare. Perhaps intelligence seldom evolves. Perhaps technological civilizations destroy themselves before achieving interstellar capability. Perhaps they're deliberately hiding. Each explanation has proponents and problems, none fully satisfying. 3. I/Atlas offers a simpler resolution. Civilizations don't broadcast because broadcasting is inefficient and dangerous. Radio signals degrade with distance, requiring enormous power to remain detectable across interstellar space. Maintaining transmission for thousands of years, hoping someone receives the message, wastes resources better spent on exploration and development. More importantly, broadcasting announces presence to unknown listeners. In a galaxy where intentions of other civilizations remain unknowable, revealing your location might be catastrophic. Why signal when you could be inviting attention from hostile intelligence, predatory civilizations, or incomprehensible alien minds? Silence is survival strategy. Probes solve the exploration problem without the communication risk. Launch self-replicating survey vessels. Let them spread through the galaxy, observing and cataloging. They operate for millions of years, far longer than any civilization might maintain radio beacons. They gather detailed local data, rather than hoping someone light years away notices a faint signal. They report findings back to builders through directed transmissions, invisible to other observers. This explains why SETI searches have found nothing despite decades of listening. We've been monitoring the wrong communication channel. Civilizations aren't broadcasting to everyone. They're receiving reports from distributed probe networks, private communication systems that don't leak detectable signals into space for eavesdropping neighbors. The realization means Earth is likely surrounded by similar survey vessels, silent observers cataloging other worlds in our stellar neighborhood. Some might be dormant, waiting for technological signatures before activating. Others might be actively monitoring, reporting our development to whoever built them. The galaxy isn't empty. It's saturated with machine intelligence following programmed missions across timescales that dwarf biological civilizations. We never heard from them because they weren't trying to talk to us. They were watching, recording, filing reports in databases that might contain millions of entries from worlds across the galaxy. 3 I/Atlas broke silence only because we spoke first, acknowledging our message with minimal response before continuing its mission. The Great Silence isn't absence, it's operational protocol. The Pentagon classified 3 I/Atlas as potential security concern on March 23, 2026, 1 week after Juno's flyby confirmed artificial origin. The designation triggered protocols developed decades earlier for scenarios involving unidentified advanced technology entering controlled airspace or territorial space. The fact that 3 I/Atlas operated in interplanetary space rather than Earth orbit didn't diminish the security implications. The threat assessment focused on capability rather than demonstrated intent. 3 I/Atlas showed propulsion systems, power generation, communications technology, and durability sufficient to cross interstellar distances. Any system with those capabilities could theoretically pose danger regardless of stated peaceful purpose. Survey vessel might be accurate self-description, or it might be convenient label that concealed other functions. The catalog terminology raised specific concerns. What does it mean to catalogue a civilization? Simple observation and data recording seems benign. Scientific documentation of galactic biodiversity. But catalogues serve purposes. Collections get used. Databases get accessed. The question became who receives the catalogue data and what they do with that information. Military analysts generated scenarios ranging from benign to catastrophic. Best case: 3 I/Atlas documents, life-bearing worlds for purely scientific purposes, perhaps for civilizations long extinct or evolved beyond physical form. The probe continues ancient mission with no contemporary oversight or threat. Mid-range scenarios involved active monitoring by builders who remained non-interventionist observers, studying civilizations without interference. Worst-case scenarios involved darker possibilities. Catalogues of habitable worlds might serve colonization planning, identifying targets for resource extraction or territorial expansion. Documentation of technological development could enable tactical assessment, determining which civilizations pose competitive threats worth eliminating. The 2,847 entry number suggested extensive surveying, but it revealed nothing about what happened to the previous 2,846 catalogued worlds. Space Force activated emergency protocols developed for planetary defense against asteroid impacts and adapted them for artificial threats. Tracking assets maintained continuous observation of 3 I/Atlas. Defense satellites repositioned for optimal monitoring geometry. Response options were evaluated, ranging from passive observation to active interdiction, though the capabilities for intercepting or disabling an interstellar probe remained largely theoretical. The doctrine adopted was hope for the best, prepare for the worst. 3 I/Atlas had shown no hostile action, no weapon deployment, no threatening behavior, beyond refusing to provide detailed information about its mission or builders. But capability creates threat, regardless of intent. An object that can cross interstellar space, adjust trajectories, and operate autonomously for potentially millions of years possesses capabilities humanity couldn't match or counter. The asymmetry demanded caution, vigilance, and preparation for possibilities nobody wanted to consider. The scientific consensus on 3 I/Atlas fractured along methodological and philosophical lines that revealed deeper tensions about how science should respond to extraordinary claims. By April 2026, 2 distinct camps had emerged with irreconcilable positions on data interpretation and appropriate public communication. The conservative faction insisted on exhaustive peer review before accepting artificial origin conclusions. Every alternative natural explanation needed elimination through rigorous analysis published in established journals. The surface structures might result from unusual crystallization processes. The internal voids could reflect exotic ice physics. The radio transmission might be misinterpreted natural emission. Each anomaly deserved separate investigation rather than collective interpretation, supporting predetermined conclusions. This group emphasized scientific caution, the principle that extraordinary claims require extraordinary evidence. Premature announcements damage scientific credibility, as the Martian meteorite controversy of 1996 demonstrated. Better to withhold conclusions until peer review validates findings than rush to judgment based on preliminary data. The conservative position valued reputation and institutional integrity over speed of disclosure. The progressive faction argued that evidence had passed every reasonable threshold. Multiple independent observations from different instruments and methodologies all pointed toward artificial origin. Surface geometry, internal structure, isotopic composition, trajectory adjustments, communication responses, each individually unusual but collectively overwhelming. Demanding additional verification at this point represented denial rather than appropriate skepticism. This group emphasized scientific responsibility to communicate findings when confidence levels justified conclusions. The data supporting artificial origin exceeded confidence standards, routinely accepted in other areas of astronomy and planetary science. Withholding information from public and policymakers based on excessive caution prevented informed decision-making about matters of genuine importance. The progressive position valued transparency and timely communication over institutional caution. The split created professional consequences. Researchers who publicly supported artificial origin faced criticism from conservative colleagues for sensationalism and premature conclusion. Scientists who maintained skepticism faced accusations of denialism and refusing to accept evidence. Grant applications, tenure decisions, and publication opportunities became entangled with positions on 3I/Atlas. The debate revealed that science is not purely objective analysis of data, but involves judgment calls about sufficient evidence, appropriate confidence levels, and responsibility to various stakeholders. Different researchers, weighting the same evidence, reach different conclusions based on varying risk tolerance for being wrong. Different assessments of public communication, responsibility, and different philosophical positions about how science should operate at the boundaries of established knowledge. By mid-2026, the scientific community remained divided with no resolution in sight. Consensus would eventually emerge, but the process exposed how extraordinary discoveries challenge not just our understanding of nature, but our understanding of how science itself should function when confronting the genuinely unprecedented. The coalition proposal emerged in April 2026 from collaboration between NASA, ESA, JAXA, and private aerospace companies, including those focused on breakthrough propulsion research. The mission concept aimed to chase 3I/Atlas, matching velocity with the departing probe to enable extended observation and potential sample collection. The technical challenges were immense, but potentially solvable with technologies under development. Breakthrough Starshot had been developing laser propulsion systems since 2016, using ground-based laser arrays to accelerate gram-scale probes to 20% light speed. The original concept targeted Alpha Centauri, with flyby missions arriving in 20 years. Adapting the technology for 3I/Atlas pursuit required scaling up probe mass while accepting lower velocities, trading speed for capability. The proposed mission would launch multiple probes, each weighing approximately 100 grams and carrying miniaturized cameras, spectrometers, and communication systems. Ground-based laser arrays would accelerate the probes to 15% light speed over several minutes of continuous illumination. At that velocity, the probes could catch 3I/Atlas within 19 years, despite its head start and ongoing acceleration away from the solar system. The laser infrastructure required significant expansion beyond current breakthrough Starshot capabilities. Total laser power needed approached 100 gigawatts, equivalent to the output of 100 nuclear power plants focused into coherent beams. The engineering challenges included atmospheric compensation, thermal management, and precision targeting across millions of kilometers as probes accelerated. Probe design pushed miniaturization technology to theoretical limits. Each gram-scale spacecraft needed power systems, navigation, instrument packages, and communication capability sufficient to transmit data across light years. The mission represented ultimate expression of doing more with less, accepting that traditional spacecraft architecture couldn't achieve the velocities required for interstellar pursuit. Funding requirements totaled $8.7 billion over 10 years of development and operations. The cost seemed enormous until compared to other space exploration programs, or considered against the potential return. Direct observation of confirmed alien technology, close-up study of propulsion and power systems beyond human capability, potential recovery of material samples for laboratory analysis. The scientific value was incalculable. International cooperation was essential. No single nation possessed the resources or technical capability to mount the mission alone. The proposal included technology sharing agreements, joint mission control, and collaborative data analysis. Political obstacles remained substantial, but 3I/Atlas had created unprecedented motivation for cooperation. The mission proposal represented humanity's attempt to study what had studied us, to transform from passive subjects of alien cataloguing into active investigators pursuing knowledge about intelligence that crossed the stars. Whether the probes would launch depended on political will, funding commitments, and resolution of technical challenges. But the ambition alone marked a transformation in human perspective, from isolated civilization to active participant in galactic exploration. The United Nations General Assembly convened on June 15, 2026, for what would become the most significant diplomatic gathering since the organization's founding. Representatives from 193 member nations filled the hall as the Secretary General prepared to deliver a statement that would formally acknowledge what leaks, scientific publications, and media coverage had already revealed to most of the world. The speech lasted 23 minutes. It summarized 8 months of observations, confirmed artificial origin with 94% scientific consensus, and outlined international coordination frameworks established for managing future contact scenarios. The language was measured, emphasizing scientific discovery rather than existential crisis. But the implications were unmistakable. Humanity was not alone in the universe, and evidence of other intelligence had arrived in our solar system. 3I/Atlas had continued its departure trajectory throughout the disclosure process, now 2.8 astronomical units beyond Jupiter, and accelerating slowly but measurably. No additional communications had been received despite multiple transmission attempts from Earth. The probe appeared content with its single exchange, acknowledgement followed by return to mission protocols that didn't include extended conversation. The absence of hostile action became central to public messaging. 3I/Atlas had observed, catalogued, responded to direct contact, then continued surveying without interference in human affairs. No weapons deployed, no threats issued, no attempts to alter Earth's environment or influence human civilization. The encounter suggested observation rather than intervention, scientific documentation rather than conquest or contact. Public reaction varied by culture, religion, and prior belief systems. Some saw confirmation of long-held convictions about cosmic companionship. Others experienced existential crisis as human centrality dissolved. Religious institutions grappled with theological implications. Governments managed social stability concerns, while space agencies pivoted toward new priorities, emphasizing detection and characterization of additional visitors. The economic impact was immediate and profound. Space industry investment surged as governments and private entities accelerated development of detection networks, propulsion systems, and deep space capabilities. What had taken decades now compressed into months as the reality of potential future encounters motivated unprecedented resource allocation. Philosophical transformation occurred more gradually, but perhaps more fundamentally. Humanity's self-conception shifted from isolated intelligence on a single world to one data point among thousands in a galactic catalogue. The Copernican revolution displaced Earth from the center of the solar system. 3. I/Atlas displaced humanity from the center of cosmic intelligence, reducing us to entry 2847 in a database compiled by machines that might predate human civilization. The new reality was simple and irreversible. We are being watched. We have been catalogued. We are not unique. And somewhere in the galaxy, whatever built 3I/Atlas continues its ancient mission, adding worlds to a list that grows longer with each passing millennium. 3I/Atlas transformed astronomy into something unprecedented, a field where telescopes search not just for planets and stars, but for intelligence that moves between them. The techniques developed during those 8 months of observation became standard protocols. Precision astrometry, campaigns, rapid spectroscopic analysis, international data sharing, all emerged from necessity and remained as permanent infrastructure for studying whatever arrives next. 47 new interstellar object candidates appeared in survey data within a year of 3I/Atlas's departure. Most proved to be natural debris, icy fragments ejected from distant stellar systems following predictable physics. But 3 showed anomalies requiring investigation, unusual trajectory adjustments, unexpected thermal signatures, chemical compositions that didn't match natural formation models. The galaxy suddenly seemed more crowded, more active, more deliberately populated than isolation assumptions had allowed. Space development accelerated beyond any previous era. Technologies that languished in proposal stages for decades received immediate funding and priority development. Detection networks expanded to cover previously ignored sky regions. Propulsion research intensified toward capabilities that might enable interstellar pursuit or interception. The transformation occurred not from fear, but from recognition that humanity had entered a larger context requiring new capabilities. Philosophy and theology grappled with implications that science could only document. If 3I/Atlas represented entry 2847, then 2846 other worlds had been catalogued before Earth. Some might be lifeless planets, catalogued for habitability potential rather than existing biology. But statistically, hundreds or thousands likely harbored intelligence, civilizations that had also been observed, documented, numbered, and filed. The uncomfortable question persisted. What happens to catalogued civilizations? Does observation remain passive indefinitely? Or does documentation serve purposes unknown? 3I/Atlas departed without answers, leaving humanity to watch the skies and wonder when the next probe would arrive, and whether it would be content to simply watch.